Ben is here.
Hi, Doug.
How are you, my friend?
I'm pretty good.
Outstanding. Just got out of a meeting that was boring, and instead now I got to do engineering. This is so much better. All right, we're going to let the stragglers come in. I'm going to show you a couple of cool things right now, just related to what we've been discussing, but that are also demonstrations that I've done in class whenever we're face to face. But but I want you to watch this because this is kind of neat, and it also will teach you some things. So here is a kayak pinned on a rock. And in order to get that off you from the bank over here, you need to get a rope on that thing and pull. So let's say you do that. Let's say you get a rope on this thing and you start pulling. Well, you might be able to appreciate that with all of the force of the water pushing against it, sometimes that isn't enough. And I've had this happen before with boats and sadly with bodies. But you can only pull, I don't know, 100 pounds. I don't know. How hard can you pull? I'm not sure, 100 pounds maybe. And water is just so strong. It's one of the things we don't have time to talk about here, but it has a squared effect on the strength. So one of the things you'll get into later on in your studies is wind, how much force wind puts on a building and so forth. And so it might not be enough. And so here's what we do. Here's what we do to fix that. So we say, okay, darn, that's not going to work. So if you can find a tree or a rock or something nearby that you can kind of tie this to, that isn't going to work. Go away. Let's switch colors. Then ideally you put a pulley here and you strap it around a tree. Now by itself, that doesn't do anything. In other words, if you were to pull off in this direction, if you're pulling at 100, that's still just pulling at 100. Do you agree with that? So pulley doesn't really change anything. You have 100 everywhere. That's what cables around pulleys do. You guys hearing me okay? I'm freezing a little bit. You guys hearing me okay now? I can see you guys are freezing, so I know something's wrong with my end.
Yeah, you can hear you now. Yeah, the audio is just those were like teensy bit, but it's good.
So watch this. So here's something. Actually, I'm not going to tell you what it's called because I want you to figure it out yourself. But if you take that pulley and run it around the corner and back up to the rope again, I want to see if you can figure out what happens here. So what I carry with me when I'm kayaking is I carry two pulleys. One I put right here, and the second one I put right here. And if I can't pull with 100 pounds, then I wrap this around this, and then I pull here. Now, of course, you should look at that and say, what is that second pulley attached to? It's just floating in midair. Well, the answer is it is attached to the previous rope.
I couldn't hear you for a bit there because you were
okay.
froze.
You please let me know that because I just got a message pop up that said my internet's unstable.
No.
So I add that second green pulley to the system and attach it with a kind of a cool knot called a prusik. I wish we had the ability to do this in class so I could show it to you. But what I want to know from you is if I now apply my 100-pound pull to this, now how much of that goes to the boat? Can you figure that out?
So what is the Prusik doing? Is that like just attaching to the rope there, or
Literally just attached to the rope. It's kind of a knot that you attach to the other rope. So would you agree that there's 100 on this rope? And what's true about ropes and cables? Well, they're 100 everywhere then. They're going to equalize that. As long as the pulley is relatively frictionless, then that's going to be 100 everywhere. So does that do any good?
Will there be 200 because there's 100 that's attached to that, and then 100 attached to the other?
Yeah, think free body diagram. If you're to draw a free body diagram of that pulley right there, does it make sense you have a force pulling this way and a force pulling this way and a force pulling that way? And so since these two are 100, then this one would have to be 200 in order for that not to move, right?
Mm-hmm.
And those are basically straight. I mean, I've drawn them at a slight angle, but they're basically straight. So that means this is actually 200 right here. So what is the boat getting then? If you, again, draw a free body diagram of this Prusik right here.
Oh, so at that point there. Well, then it gets the 200 and the 100 from the other.
Right. That's exactly right. So from the Prusik's perspective, it's got 100 pulling over here and it's got 200 pulling over here. So therefore it's got 300. So I just tripled my effort there. So this thing is called a Z drag or a 3-to-1. And you see why it's called a 3-to-1? Because that setup triples whatever force you can provide. And so, and again, there's no limitation to this 100 right here. If you can get 3 people pulling on it and make that, 420 or whatever, then great. You get triple of whatever you do. And so that's really cool. So I've pulled kayaks off of rocks using that technique. So it's really cool. But again, it illustrates the concept of what we've been talking about, which is a free body diagram and looking at something that's confusing and being able to break it down. And so notice there's 2 free body diagrams here, and they're really focused just on each joint or each spot. And so there's free body diagrams you can put everywhere in this situation. You could even put a free body diagram over here on this point. And of course the tree would be being pulled on with 200 based on what we just discussed. And so, but it's a tree, right? So it's going to be fine. So that's really cool. Let me show you something else that's cool. See if you can figure this one out. So here's the rock and the kayak is pinned on the rock right here. And you throw a rope out just like before and you say, let's pull on the kayak, and you're unsuccessful. Dang, I can't pull hard enough to get that off the rock. And so what you do this time though, is you just wrap this around a tree a whole bunch of times. And now you have it tied to the tree, which of course does no good whatsoever because it's just tied to the tree. But what I want to know from you is, what if you take your 100-pound muscle that we just used a minute ago and tripled thanks to technology, and what if you came over here and you pulled on this right there with your 100 pounds? I want to give you a second to stare at that. This is called, interestingly, a vector pull. So this is something you get taught in a safety, a whitewater safety kind of a class. There's a couple of things you can do to. And let's further say, just to give you something to think about, that you have pulled this so that that angle right there is 4 degrees. My question is, why would somebody do that? What good does that do? How much force is that? What does that do for the boat? You had a question in your assignment that was like this. I think it was 23. It was really hard because it was because it had a spring on it and stuff, made it worse. But this is just a rope.
Is that like pulls in a little bit different direction, like the boat moves not like straight towards the tree, but it moves like 4 degrees, or maybe not 4 degrees, but it moves.
Yeah, you're right. The more you pull on that, if you change that angle to 4 degrees, you're now sort of pulling the boat not toward the tree anymore, but it's actually going to go straight toward that line right there. So you're kind of pulling it up, which is actually a good thing because you're trying to pull it off the rock. So you would want to pull this in the direction I'm showing as opposed to pulling it the other direction, because that would just make it pulled tighter against the rock. But the important thing is, how much force does it generate? So again, I'm asking, all I've done is draw a picture right here, but can you use what we've been talking about to take something that looks confusing and break it down? And remember, this situation is static. In other words, you're sitting there going, and you're pulling right now, and you're pulling with 100 pounds and the rope is bent out 4 degrees. And so the question is, well, if it's static, can you draw a free body diagram of that and figure out what the heck is going on? And just to make sure you get started in the right direction, your free body diagram should be focused around that point right there that I just covered up in red. So that point is static, it's not moving. Well, free body diagram, equilibrium. How much force? How much force is those other two dotted blue ropes, if you will? How much force is going to be on those to make that point static?
Mm-hmm. I think I get it. 4 degrees.
It's going to give you a second to think about that.
And that you're applying force 100, like right in the middle?
Yeah.
Okay.
The beauty of this logic is, if you stare at something like this without some training, it's confusing because there's like trees and rocks and ropes and boats and pulleys. But the beauty of a free body diagram is you look at just any point on this you want, and then you say, forget about everything else, get rid of all the boats and rocks and everything, get rid of all the rope, just draw arrows. I'm going to catch up to you so we don't run out of time. So free body diagram. This point right here has a vector of 100 pulling down, and there's something pulling there and something pulling there. These two forces. And you can probably appreciate, to Evold's point, if you put it right in the middle, those two forces would be the same, but they have to be the same. Why do they have to be the same?
Because they have to cancel each other, the x components out.
Exactly. Some of the forces of X have to be 0. Hence, F equals F. Now, I'm going to erase this, but just to kind of show you something. If you pulled way out of center like this, does it make sense those two forces wouldn't be the same? And the reason is because they're not at the same angle. So you're going to get the sum of the forces in X canceling out, yes, but they won't be the same because they're not at the same angle. So if we set this up and pull in the middle so that, in a sense, maybe I should add that to the drawing, so that they're both 4 degrees, then those forces would be the same. So that kind of takes care of that. But then if you look at this, if you look at your drawing then, and you think, okay, well, what do I know? I need the sum of the forces in Y to be 0. And so I have 100 going down. And so then what component, thanks to trigonometry, what component of that F then is actually going in this direction? Well, since that's 4 degrees and this is F, and I need the horizontal component of that, I could say that that horizontal component is modified by the sine, isn't it? By the sine of 4 degrees. Do you agree with that? And then there'd be another one of those, right? For the one on the other side. So rather than say times 2, just so it looks better in the notes, I'm going to write the whole thing out again. And of course, I need that thing to be equal to 0. Well, again, we see that and we think, okay, awesome. I can solve that. There's only one unknown in it. But interestingly, what do you get for the answer to that? What is F? You get 717 pounds for your 100-pound pull. Now, again, that's very dependent on the angle of 4 degrees. As soon as you get it pulled out to where it's 20, you're getting less and less and less. And so it might be fun to play around with that a little bit. So when you tie this off, you might not have to, if you tie it off really weakly, you might not have to pull very hard to get it to 4 degrees. Like you might only pull with 2 pounds of force to get it to 4 degrees. In some respects, the best thing you could do here is actually, if you pulled this tight and it still did not come off at 300 pounds, if you took this and tied it off, does it make sense? This rope right here would be super tight now, way tighter than you would get it by just trying to wrap it around a tree. This would be like, you could play it like an instrument now. And so when you pulled on this rope in that vector pull sort of a fashion, that's going to make more of a difference. So my point is, by the time you get to 100 pounds of pull, that might not be 4 degrees. It could be clear out at 40 or something ridiculous, and you're not going to get any pull out of it at all. So this is not as simple as it looks to actually set up and do. But this is an example of, like, you know, how people use what we're talking about to kind of do cool things. So the two topics here are Z-drags and vector pulls. So it's just kind of cool. Thought you guys would be interested to see that. In my regular class, I actually bring all that equipment in and set it all up and like put someone in a chair, and then we hook it to the chair and you pull them across the room. You can kind of feel like, wow, I'm really not pulling near that hard. You try to pull them like just with your hands on the carpet and they don't want to slide, and then you hook up that Z-drag and pull, and you can totally feel that it's like a third as hard to pull them across the room as it was before. Any I don't know, thoughts, comments on that?
That's cool because that problem came up in physics. It was like a little short problem. I didn't really understand it at all, but now I do. So that after
well, I think it takes something practical, because we did not have time to talk about pulleys enough, but I think drawing that, and you know, especially if you can set it up in a room, is just so powerful. I'm glad that clicked for you, Ben. For you not to understand something, that means, both of you guys for that matter, that means the teacher didn't do their job, because you guys are both sharp. Okay. So two other things I want to do today. One of them is get to this question, which is similar. Just another example that lives in chapter 5 that gets at equilibrium. How many, I want to go slow with this. Don't even read the question. How many free body diagrams do you see there that are possible to draw?
I guess we could draw them around any point, right? So 3.
Yeah, you could, like this would be one for sure, because I can think, hey, look, weight pulling down, and then 2 other members either pulling or pushing. I don't know, but it's like that'd be a good spot to draw one. Here would be good, but notice there's not a lot going on there. Notice that point doesn't know C exists. Does that make sense? And the same would be true for over here. If I'm over there, those are all good options. And an engineer's got to draw all of those. Do you understand why? Because if we determine, for instance, again, I haven't read the problem, but if we determine that was pulling at 1,000 pounds, then don't we have to go down and look at that support right there and kind of figure out, is there the equivalent of 1,000 pounds of bolts and glue and whatever holding that to the block, if you will? So do you see what I mean? Like we sort of need all of them. We got to draw all of them. So I find that a little confusing with these problems, just because they sort of act like there's no choices there. There's all kinds of choices. There's even a free body diagram right here. Do you understand that? Why would there be one right there? Well, you are attached to that weight. Like, is it possible you're not U-tied, so to speak, or your swaged anchor like comes apart? I can see that ball falling off, and so maybe the ball weighs 1,000 pounds, but is the cable capable of pulling back? Now notice that's really easy in the sense that this is facing straight up, so I don't have those components of X and components of Y to think about. It's not all confusing. But yeah, every single point, and even the ones that aren't even labeled, could deserve a free body diagram. So it's kind of interesting. So anyway, what the heck do they want me to do here? What's the problem? They want me to determine the magnitude of the force at pin A and in the cable BC needed to support the 500-pound load. And so, okay, cool. They're telling me that. That's 500 pounds pulling straight down. I'm glad it's pounds because I don't have to convert it. Pounds are force. I don't have to multiply it by 9.81 like you do if it was kilograms, right? If it was a mass. And they're saying the boom AB doesn't weigh anything. Now, what I'm going to show you for a demonstration today is that's kind of dumb. AB cannot not weigh anything. Like, it's holding a weight. It's got to weigh something or it wouldn't be strong enough. And they're just saying that to, make my life a little easier. But I'm going to give you a demonstration today that we're going to kind of run all the calculations for, that's just like this. It's doing a job, but we're not going to neglect anything, and we're not going to be given stuff. We're not going to be given any weights, any lengths. Like, we got to go get them all ourselves. So that's kind of cool. So I don't know, like they said, determine the force at pin A. So part of me wants to draw my free body diagram at A, but why is that a bad idea? Why is it a bad idea to draw a free body diagram at A?
Well,
Go ahead.
Oh no, that's okay. Go ahead, Lennon. Sorry.
So I think maybe because AB force going towards the A.
It's okay that it's going towards the A.
Is that okay? Okay.
Okay, that AB is going towards A. It's not that we can't do it, but why is it not as helpful as maybe some other options? The main reason is that load A doesn't know that load's there. You understand that? A free body diagram is a point with a bunch of arrows on it a lot of times. So, you know, just looking at a particular point. So I'm thinking if I move up here to B, that I got a lot more going on up there. I got arrows going everywhere. Now, you know, do I have to go at B? I don't know. I don't know. But the point is there's not a right answer to these things. You can draw lots of them. But I'm just thinking if I go to B, a free body diagram at B, I'm gonna have a lot of stuff going on. I guess what I'm trying to encourage you to do here is just to think. There's all kinds of ways to do a problem like this. Just write stuff down, and maybe what you wrote down, maybe you do a free body diagram at A. But because 500 is not involved, you won't be able to make many calculations to it. So it certainly makes sense to start at B, I think. So I'm going to say free body diagram at B. And by the way, there's a part of me that says, since I know some lengths and angles here, there's a part of me that wants to draw this triangle right here, that kind of triangle that's made by ABC, and start doing trig to them. Because I know angles in them, and so I could do trig to figure out lengths, and I could find all the lengths and angles and everything involved, and there's part of me that wants to do that too. And I don't really know which one is. Maybe I'll have to do both. I don't know. But the first thing I'm going to do is try to do what we did, well, what we just did a second ago, which is pick a point and see if I can get it to stay, well, static. So I need the sum of the forces at B to be 0, and I know I have 500 pounds there, so let's go see what's going on here. So there's B, 500 pounds on it. And here's force, I'm going to call it force A, because it's aiming toward A. And there's force C. And so I need all of that to add up to nothing. And remember, it's a good rule of thumb to just consider them all tension. Do you agree I drew them all in tension because I drew the arrows away? It's a little dangerous when there's a lot more forces. It's kind of dangerous to guess. I'd be willing to bet you could do it here. I'd be willing to bet you could see that AB is getting smashed, and so AB is under compression. But if you pulled down on B, BC is getting stretched. I'd be willing to bet you could see that here. But I'm just not going to assume that. I'm just going to let the math take care of itself. Okay, well, great. Let's start setting up some of our forces. And again, I've got moments to calculate. So, you know, I don't even know which one to start with. So unless I was really good at this, maybe if I was really good, we would start with the right one. But, you know, I don't know. Let's just write them out. Some of the forces in X need to be 0. Well, 500 is not competing. 500 is not part of that. So I got force of C pulling left. And I'm going to kind of add to my diagram up here. Since that angle's at 22, this angle up here would also be 22. So therefore, my force of C, if I modify it by the cosine of 22, that's the horizontal component of C. And I see it's pointing left, so I'm going to assign a negative to that. And the same thing happens with A. A, because that's 35, that means this angle up here is also 35. So same thing happens. I end up with minus force of B. Sorry, A. Minus force of A modified by the cosine of 35 degrees. And that's all the forces, and those have to add up to 0. I'm not happy because there's force A and force C, and I don't know. Can't solve one equation with 2 unknowns. Again, this is just one way to do it. So instantly interrupt and chime in about, you know, I was going to do it this way, or, you know, why did you do that? Please speak up on that kind of stuff. Okay, so not happy. All right, well, maybe we'll be luckier with Y's. Or maybe with Y, we'll get another 2 equations with the same 2 unknowns, and then we can solve that. So let's see what's going on with Y. Well, I've got that 500 going down. And then I've got force of A and force C also going down. Everybody's going down. So just like before, force of C, except for force of C would be modified by the sine of 22. And the force of A would also be modified, but it'd be by the sine of 35. And again, I can tell this isn't right because they're both pulling left, they're both pulling down. They can't both be pulling down. All three of them are pulling down. There's no way this thing is static. I've got one of them wrong. One of them is certainly not in tension as I have guessed. So I am happy now. Hey, 2 equations, 2 unknowns. I can solve that. But before I do that, I'm just going to keep on going and think about moment here. Let's see. Well, I guess considering I didn't draw, since I'm considering B about a point. Could I do moment someplace? I can't say the sum of the moments around B. Do you understand why I can't say the sum of the moments around B? Why is that weird?
Not have enough distances.
Yeah, every single cable or pipe is touching B, therefore they're all 0 distance away.
Oh, that's true. Yeah.
But I could go around A if I wanted to. All I'm trying to do here, as I said, I got lucky in one sense because I just got 2 equations, 2 unknowns. So that would work fine. I don't have any reason to do what I'm doing right now. I'm just thinking out loud because this is how you solve problems. You don't just stare at something and immediately know what to do. You have to say, hey, I got all kinds of things to do. Let's do them all. So some of the moments around A would have to be 0. Why is that actually kind of cool? Or why would that make sense? Or why would that be possible? Well, notice this member is pointing right at A, so that's causing no moment at all. But isn't this 500 pounds? Isn't that 500 pounds there? That distance away? So that's causing clockwise rotation, isn't it? Isn't that 500 a distance D away? I don't know what that is, but can I do trig to figure it out? And then this force over here, if it's pulling back in this direction, I got a couple choices. I could either say, well, maybe I can use trig and find that distance D right there because that's perpendicular. But that looks hard to figure out. I don't know, maybe not. Maybe that's not hard to figure out. The other option would be to take that force and, well, do what we did a minute ago, like break it into its components. Isn't that the force in towards C, but in the X direction? Well, now there's its distance perpendicular. And then its force in Y, isn't that right up here? Force of C in the Y direction. And isn't that distance going to be all the way across here? That looks easier to me because we already found the force of C and X by multiplying it by the cosine of 22 and so forth. But let's come back to that. Let's finish what we did first, and we'll come back to that in a minute. Because I'm just wondering, like, do they both work? Are they? I mean, I don't really need them in one sense because I'm looking up here at 2 equations, 2 unknowns. So let's see, if I use a matrix on this, I'm going to use my graphing calculator because I'm not in the mood to do algebra. Plus the numbers are so weird. So if I do a matrix, this is my force of A column, this is my force of C column, and this is my constant. So force of A, I have negative cosine of 35. Notice I kind of put it in a different order. It's kind of up above it was C and then A, but I was just thinking alphabetical. So negative cosine of 35. The force of C is negative cosine of 22. And that's all equal to 0. And then the blue graph, force of A is negative sine of 35. Force of C is negative sine of 22. And what do I put over there for the constant?
Be positive 500 because it was negative before.
Yeah, remember it's got to be on the other side. So I've got to move it over here, which would actually make it a positive 500. So that's a 2x3 matrix that I'm going to stick into my graphing calculator now and quickly get the answer to. You're welcome to do the same. I'm not going to, I think I've showed you this enough that I'll do something else if you want me to. So I'm saying 2x3, I'm saying negative cosine of 35. And I've got to get into degree mode. Negative cosine of 22. 0, negative sine of 35, negative sine of 22. This is very exciting. And then 500, and then second matrix, go to math, reduce the echelon form of that matrix, and I get that, well, the first column, which was force of A, I get force of A equals negative 2060.85. I'll call it 0.9. And I get force of C equals 1820.7. What does that mean? What does that mean? What should you answer now that you're, and I'm kind of not reading the question right now. I'm just trying to figure out what's going on in that picture. Really, it means that force A is, what's the name for that force? What do I call that? Since that came out negative.
In compression then?
Yeah.
What'd you see?
By drawing the arrows away, you're assuming tension. In other words, you're pulling on something. If you pull on something, you're tensioning it. You're pulling their arm off or whatever. And this says wrong, it was negative. So that means compression. And for C, we got right. I'll call it 1821. Positive, so it's tension. I don't know how good your spatial awareness is, but that's what we just discussed a second ago. If that weight was pulling down, can you see that that member AB is being shortened by that process? That's compression. That's what we just got. Notice they even drew it that way. Can you tell that they drew AB as a pipe? Or as they drew BC as a cable? So notice that's remarkable because force of AC, the force that's on AC, I'm sorry, what am I saying? A. The force that's on AB is actually 2,000 pounds. It's 5 times as much force. I mean, isn't that surprising? It's so huge in order to lift that ball out there, to reach out over the edge of the dock and lift that heavy thing off of the ship. That's got to be 4 times as strong as the weight it's lifting. I mean, isn't that kind of amazing? Let's see, I don't even know what questions they asked. I'm going back to look now, and I'd encourage you to do the same thing. Just take the drawing, see what they gave you, and just start figuring stuff out. If you do that, then you'll be able to answer whatever questions they ask. They said, determine the magnitude of the force at pin A. The magnitude of the force at pin A. Notice they didn't say direction. And I guess that's because, well, they already told us that 35 degrees. So I found it, 2061. Like the very fact that that pipe is there means it's pulling in both directions at the same exact amount. It's being smashed. That force is being transferred right down to that pin A. And in cable BC. Well, I guess I found that too. So my first method that I tried worked. It's 2 equations, 2 unknowns. But I'm wondering what would happen if we tried this moment idea. Like we never needed moment here. So I'm wondering if we tried from the start, if we had done the moment around A, I wonder what that would have yielded. So let's go back up here and do a little bit of trig so we have all the distances we need. Let's see. The cosine of 35 would be adjacent this D right here over 8. So 8 times the cosine of 35, which is 6.55. And similarly, this length over here, this distance, would be 8. That'd be sine of 35 is D over 8. So that'd be 8 times the sine of 35. So that's 4.59. And let's see, what else do I need? Do I need anything else? I don't think so, but we'll go back and figure it out later if we do. Again, stop me because I'm not doing this. I'm doing this so that you can think. I already know the answer. I already know how to do this. So some of the moments around A, well, I got that 500 pounds. I got this 500 pounds and it's a distance from A perpendicular of 6.55. So it's 500 force, 6.55 feet, foot-pounds. And that's going in the negative direction. Do you agree with that? It's going counterclockwise. I'm sorry, it's going clockwise, so it's negative. So negative 500 times 6.55. Then, as I said, I'm going to go ahead and write this all the way out. We've got the horizontal component of force BC, and its distance from C is that 4.59 we just calculated. So that's good. So it's force of C in the X direction times 4.59. And what kind of rotation does that cause around? What is that causing around A? Well, isn't it going this way, which is actually positive? Do you agree with that? So force of Cx plus force of C in the X direction times 4.59. But then don't I have force of C? Go away, go away. How do you go away? I never remember how it goes away. Then we have the force of C, which is pulling straight down over here. And notice it's the same as the 500. It's like in the same exact, it's actually lined up. It's actually right on top of that cable. And it's also a distance of 6.55. So it's kind of right there working with the 500-pound ball. And it's causing, again, clockwise rotation. So force of C in the Y direction times 6.55. And that's all of the moments on this, and I need those to add up to 0. Now I would be unhappy with this because it's got 2 unknowns, except for, as you saw just a second ago, didn't we say the force of C in the X direction was, well, the force of C, but just modified by the cosine of 22? Wasn't that true? And wasn't force of C in the y direction just the force of C times the sine of 22? So now I just have the force of C. One equation, one unknown. I like this one better. Actually, this was a better idea in my opinion. Now the only downside is I'm going to get the force of C. I think if I don't screw this up, I'm going to get 1821 because we already got 1821. But I'm still going to have to move on and get the force of A somehow, right? So let's punch all the numbers in on this and see what we get. I'm going to slow down and actually kind of do the algebra a little bit. Let's see, what's 500 times 6.55? I got about 3275, and that'd be negative, so I'd have to add that to the other side. And on this side, I'd have cosine of 22 times 4.59. And that's positive. And then I'd have sine of 22 times 6.55, and that's negative. So I'm going to put those together. 4.59 times the cosine of 22 minus 6.55 times the sine of 22. I got 1.802. So I got 1.802 force of C. So now if I take 3275 and divide by 1.802, oh my goodness, I got the same answer. Well, I didn't quite. I got force of C is approximately 1817. Why did I miss it?
Too much rounding.
Yep, just rounded a little too much early, and really the fault was probably these 6.55s. Now normally you'd think, hey, that's pretty decent to round there, but remember we ended up multiplying it by 500. So had we carried that out one more decimal place, then we would have got a better answer. Now in the scheme, in the larger scheme of engineering, do I care that one of those is 1817 and one of those is 1821? No, I don't. Because that's 4 pounds. Like I'm going to be designing this to hold a lot more than this. Like I'm going to be a lot more careful than that. Does that make sense? I'm going to be doubling this answer anyway, or something of that nature. On a test, because I'm not paying attention to rounding. Those are both full credit. I could care less. But isn't that cool that you can just totally do this a different way and yet get the same exact answer? That's what I would like, because I want to teach you how to think. That's what I would like you to understand. Don't feel like, oh no, I don't know what to do. Yeah, you do. Draw a free body diagram and just start making everything be zero. Like write them all. What else could I write? Well, I've got, notice I took that moment around A. Could I go back and redo this whole thing around C? Incidentally, and just think about this for a second, because I went around A, then that means this force right here wasn't a part of the picture. Do you agree with that? Like it ended up incalculable because its distance from A is nothing. Does it make sense if I redid this around C, then that's going to make this go away, but then this one will be here. And so what I can tell would happen is I would have the same exact kind of design that I just had a minute ago, except for I would have force of A sitting there. The answer I would have got was force of A. So I could have set up 2 separate moment equations here, and I would have got both answers by solving one equation, one unknown. Or I could set up 2 force of X, force of Y equations and set them equal to 0. It all works. And I'm just saying, I think that's so much more powerful than, you know, the teacher showing one example or you doing it away and go, okay, that's how to do it. Well, no, that's not how to do it. That's one way to do it. You can think, you can reason, you can draw pictures. If they don't get the same answer, that means you just screwed up in your reasoning somewhere. When I was learning this, I found this very hard because the teacher would show an example, or I would look in the back of the book and I would think, oh, that's how to do it. Well, not necessarily.
So I wonder realistically, because those are pins, right? So they couldn't provide any moment there.
That's exactly right.
Right? So the ball would just fall unless something else, unless there's like a system that's like controlling that.
Yeah, notice in the free body diagram, because those are pins, that's why I didn't come back and say, oh yeah, that's a fixed support. So there's some moment being provided right there. That's why I didn't add that, because it's a pin. Good observation.
So you can still use the moment reasoning, but you realize because that's a pin, it doesn't actually provide that moment there because it.
Yeah.
Do
Do you understand if that would have been a fixed support, if they would have showed that as welded, then I would have had to add that right there, that moment support that joint would have provided. I would have had to add that to my formula down below, and that would have made it confusing because then there'd be two unknowns. Because now I don't know how much is being provided by the cables and how much is being provided by that fixed support. Just for the fun of it, this is 532. Let's go look at something real quick. So because I'm connected to this class through the Pearson company, I have access to the solutions, which you are welcome to see whenever you want to. If you and I are looking at them together, let's just see how he did it. And I'll tell you, when I was learning this, I had like his answers did not help me. They hurt me. I didn't look at this ahead of time, but I just want you to stare at this and see if you can see what he did. So he did something kind of cool. Do you see how he said, hey, horizontal, I'm going to call horizontal that right there. That's horizontal. See how I drew over here and he said X? I'm going to call that horizontal, and then that would make that vertical. Now, as a result of doing that, do you notice over here that his angles are all screwed up? They're like different than our angles. He has a 13, not a 22. And so you see what I mean? Like my goal here is not to figure everything out here, but notice he started with moment and he went around A just like we did coincidentally. And this is kind of a good habit to get into, but he made a note here to say, hey, this is positive. Do you see what I mean? I'm going to call that positive. Well, that's the convention. To go counterclockwise is positive. And so he's just telling us that, telling himself that. And so although he did it differently, by setting up that moment equation first, he produced one of his answers, force of BC. Notice he called it 182 kips. You shouldn't be surprised by that. What did we get? We got 1,821 pounds. That would be 1.82 kilopounds. So you'll never see, you're going to see kips when you do engineering. There's never pounds. Nobody designed something that's so small it's less than 1,000 pounds. So it's always kips, kilopounds. Then, because he had one answer, force of BC, he said, how am I going to get the force? And by the way, I kind of like that. Notice he called it force of BC. I just called it force of C. I think that's kind of cool because it's really obvious what you mean by that, by listing both points. I think he's got a point there. Then he went back and said, okay, well, notice his little convention here. He actually drew the line at an angle to match over here. And he said, that direction is what I'm calling positive X. Isn't that kind of cool that you can mess with that if you want to? What did that allow him to do? Well, notice his AX over there. Notice that did not have to be modified then. He just said, yep, that's a number, like it isn't modified by anything. Now he had to modify all the other ones. Notice a minute ago for us, wasn't 500 going straight down? Well, because he turned the whole axis, now 500 wasn't 500 anymore. It had to be modified by the sine of 35. But my point in showing you this, and again, I didn't really prepare this, is just, we just did this 2 ways, and now we're looking at even a 3rd way. You're trying to learn to think here, not just how to get these problems correct. And so when I found myself, when I looked at his answer saying like, I'm trying to teach myself this and I'm struggling, I looked at his answer, I was like, God, this doesn't make sense. It seems so complicated. Why did you do it that way? I didn't understand it. And I wasn't confident enough to think, well, God, you could do this 10 different ways. Now I am, and I want to make sure you guys feel the same way. Don't feel like I don't know what to do. Draw a picture and start figuring stuff out. Like, they all work. You just got to make sure all the forces in X, all the forces in Y, and all the moments 0. If they are, that's going to allow you to figure things out. So cool. Okay. So I'll post those 2 things. And now what I would like to do is play around. And we're going to kind of fake the project that I did in class. And I'm going to kind of draw it exactly the way we did it in class, because last time I did this, I actually took measurements on all this stuff. And so I need to find it real quick. So what I'm looking at here is what I'd consider to be a realistic question. A realistic version of what we just did. Let's see. Okay, so in my office I have some wood. So here's the design. So this is the classroom. This is the front. This is the side view of the classroom. So, you know, the people are standing like this in the classroom. So I want to stick a beam against this wall right here. And obviously, so that was just a little piece of wood. It was like 2 inches tall and a ½ inch wide and like 4 feet long or something like that. I'd like it to, I'm not sharing my screen right now. You guys should have interrupted me sooner. Does no good to explain something if you do not show it to them. Come on, man. What I'd really like you guys to do, sorry this is taking so long. What I'd really like you guys to do is kind of as a group, see if you can just talk out loud amongst yourselves, ask me questions, see if you can, between all of you, just live, get this question correct. Come on, man. Don't have time for this. What does that say? Apple TV. Whew. Okay. So here's this stick coming out from the wall. And what I want to do, what I'm doing as an engineer here, is I'm building a crane. And so what I did in class is I took one of those physics weights and I hung it right here. And that weight was 550 grams. You've seen those little, did you play with those in physics, those brass weights and stuff that you hang on scales? So we took one of those. And so, you know, we're treating this like, hey, I'd like this to do a job. And, you know, here's this beam sticking out. And so we're going to lift this 550 gram weight off the ship. So of course, if I tried that right now, the whole thing just falls, right? So how are you going to keep it up there? How are you going to keep that there? And again, think classroom. Like I'm thinking playful here. This is not a real building or something like that. I just stuck that against the wall over there. It's not going to want to stay there. What else could I do? I want to lift that.
Try to put a book under it to support it or something.
Yeah, maybe something to support it on that other side. In my case, I kind of set it against a little bit of a rail. But of course, there's nothing to support the other side. So then I came back on the other side and said, let's put a piece of string over here. Does it make sense that would work now? Like that would stay there? And that's kind of what we did in class. I tied a piece of string to the wood. I tied it to the wall up there, and I hung this weight on it, and it stayed. Like I stood back and it was like, static. It didn't move. That's awesome. And by the way, with that force pulling on it, I didn't have to put anything over here on the wall. It just stayed over there. It was right against the whiteboard, just sitting against the whiteboard, and it stayed put because there's now force pushing against it. Now, the question is, can you calculate? And you have questions to ask me. What I want to know is what's the tension in that string? And what we did in class is I got a spring scale and we actually tried to calculate it, and then we measured it with the spring scale to see if we got it right. So there was a spring scale inside that system right there, but we'll just calculate it based on this. Now, my question to you is like, what do you need to know from me? What I did in class is I just turned people loose with tools. But if you had this hanging there and I said, okay, calculate that tension, what would you need to know to start doing what we've been doing lately? Tell me things you want to know.
We need to know that angle from the board up to the string.
Yeah, in other words, like this angle
Or
over
any
here,
angles.
this angle over here.
Yeah.
Can you
That's right.
appreciate that would be really hard to measure?
Oh yeah.
That'd be hard to measure because you'd have to put a protractor against it. So what could I measure that would get me that angle?
Well, if we assume that this is forming roughly a right triangle, if we have the lengths of every side, we can find the angles.
That's true. And so let's do that. Let's put it on the wall, and we could just use a piece of paper, right? That's 90 degrees to put it on the wall so that that's 90 degrees, and we can take all these measurements. And so I'm going to call that A, that B, and this over here, C. So now let's take those measurements. And I'm writing down the measurements we took in class when we did this. AB was 116.5 centimeters. And B to C was 150.9 centimeters. And I guess we don't really need to measure AC since we can just calculate it, right? I'm not going to tell you anything you don't ask me, but you haven't asked me enough yet, so just be aware of that.
How far is I mean, we can measure it from C to the 550 grams. How far is that distance?
Yeah, we need to know that. You are not wrong about that. So I'll call that point D. And then we can say that CD let's see, I gotta kind of calculate this. It's 19 centimeters exactly.
Okay.
What is the weight of the board?
Why do you want to know that? Good, I'm glad you asked that. I was hoping you guys would get that.
Yeah, because I mean, that force is gonna go straight down as well.
Yeah,
So that's when we're gonna like build our. I mean, when we're gonna choose our string, we need to know the thickness of it so it can hold the tension.
that's exactly right. So remember in that last problem how I kind of said that that was really lame, that they said that one member has no weight on it? That's just kind of lame. That weight is not insignificant. So yeah, what's the weight of the board? So I brought a scale to class and I took the board and I set it on the scale. What am I going to get if I set it on the scale? I don't mean the number. You don't know the number, but like, what's the reading going to be?
Like in grams still.
I
Yeah.
was gonna say weight in pounds, but because we're in the US, but
Yeah, US.
Yeah. So maybe the scale has options, like you could switch it to ounces or pounds. Maybe it'd go ounces and pounds, and maybe it's in metric.
Oh yeah, scale would be okay. Measuring weight.
I'll give it to you in the way that it was. I didn't play with it. I just turned it on and stuck it on there and it said grams.
Okay.
So that weighs 347 grams. Notice that's a pretty significant number relative to the weight you're lifting. Does that make sense?
Yeah.
That's why it's so important. If you don't include that, and that's true in the real world too. One of the things, I was just over by the hospital, and this is something we got to talk about. But there's a tower crane at the hospital right now. We got to go see that. So we got to take a field trip sometime here soon. I don't know where you guys all live and all that, but I know where Evel lives. But we should go have lunch one day. And they're one of the best food trucks in the whole valley is over there. I'll buy you guys all lunch and we'll go hang out and check out this tower crane working and talk about it.
How far is the from the BC line, the attachment? Where's the 550 grams that the weight is attached to?
You told me that earlier, isn't that? That's the 19.
Oh, that's what. Yeah, right. I asked already. That. Never mind.
The same thing? Okay, good. Just want to make sure it wasn't misunderstanding.
No, that's not the thing. Same thing. So because CD is going to be a horizontal distance, right?
Yeah,
I'm talking about vertical distance.
got it. How far down? That was in the middle of the board. Let's see. ED, did I write that down? I'm just gonna have to go off memory on that. So the whole thickness of that board is 5.2 centimeters. And the 550 was in the middle of it. I drilled a hole in that board and I hung the hooked weight. It's kind of a hook that came with that weight, and the hook weighed 50 grams, and then the weight I set on it was 500 grams. We weighed that too, by the way, just to make sure it actually was what was stamped on it. I don't know if you play with those in physics, but it actually weighed what it said to the accurate to the nearest gram. So that was kind of cool. So one of the things I'm curious about is, have you thought about attachment points? Like, how is this attached? And have you added forces at A and B correctly?
Mm,
But like, because we're going to run out of time, I'd like to talk about that for a second. Like, what's the force happening at A? If I tie that to the wall, what is that? What forces are up there that I can include?
but wouldn't it depend on who, like, what perspective you're drawing it from? Like from C, if you're drawing it around.
Yeah, you're like, you might not need it. You might not need to use these.
Uh,
You're not wrong about that.
mhm.
But because it's tied to the wall, does it make sense, and it's flexible, that it can't provide any moment? So there's no moment there, but it's tied, so it can't move up and it can't move out. So that means it is providing.
He's providing that. Yeah.
And again, I don't know what direction to draw these. I don't know, should I draw the arrow up? Should I draw it down? I don't really care. I'm just going to pick the positive convention for both of those. What about down there at B? Is it the same thing?
Well, in a more ideal world, there probably wouldn't be a, considering it's just kind of resting on the wall, it kind of implies it's not a very significant force in Y. I imagine friction still holds to some degree there.
Yeah. Now it wasn't attached, which means the wall's going to keep it from banging into the wall. So we're definitely getting a force of in the X direction, right? But then the point is, are we getting any force in the Y direction? And it turns out the answer is yes, and it's because of friction. Can you see that the cable's pulling it into the wall? Well, because it's pulling it into the wall, it does not want to easily slide. And that's the reason why it didn't fall. Does that make sense? Like if I just put this calculator against this over here, that whole end's just going to fall, right? Unless I push into it, creating friction. So there actually is a force here being provided, which is why it was able just to sit against the wall. And if you don't include that, like this problem actually doesn't work. So you may have some other arrows, different places, but again, the question is, can you draw a free body diagram of the board? That's kind of what I would encourage you to do. Can you draw a free body diagram of the board? And like get all the arrows on it. Where's all the arrows? Where's all the forces? What's since we're working in metric here, what are our forces measured in?
Newtons.
Newtons. And we're a long ways from newtons if we're sitting here with grams. So think about that. A Newton is a kilogram meter per second squared. We don't have meters, we don't have kilograms. So, warning. Feel free to mention calculations you made, ask if other people got the same things. I mean, treat this like you guys are the engineering team hired to build this crane system, and it's entirely, your own measurements and everything you're taking, but I'm the customer and I'm going to pay you $1,000 or I'm going to sue your pants off you if you get it wrong. That's how it works in the real world. So you guys check each other's work, you know, it can't just be one person.
So I got for that angle, going kind of from B to A around C, I got like 37.669 degrees. Other people get something like that? Not yet.
Come on, the brothers asked you all a good question. Answer it.
I'm checking.
Probably didn't. Yeah.
Help a brother out. It's a good question he's asking. If you don't know how, talk about it. Tell them how you did it, Ben. And that way they
So
can
I just
compare what they might have done.
Yeah, so I just took the AB over BC and the tangent of 116, inverse tangent of 116.5 over 150.9 to get that angle theta. So am I allowed to draw on the diagram here, or just to show really quick? Wait, but I got like that angle right there is what I was calculating.
Sweet. Landon, Evel, you agree?
Just 1 second. I was thinking about the forces on the board.
Fair,
On
Oh,
actual
yeah.
board.
I was trying to
fair enough. You're not all.
shape all those too, but
So, what angle you got, Ben, again?
I got like it was 37.669, so about 37.7.
Yeah, lines up with what I got.
Okay. Then did you guys get like the forces from the 550 and 347 gram things? Just the 9.81 times that, right? So, or well, the 0 point, we have to make it into kilograms first and then multiply 9.81.
I'll be the scribe. Like if you guys, I'll add stuff that you guys tell me, but I'm not going to tell you if you're right or wrong. I'm going to tell you if you're right or wrong at the end. That's all I'm going to tell you.
So I guess we should add that angle theta be 37.669 degrees.
Okay.
You were. And I can erase stuff, like go ahead and propose something you want me to add to our free body diagram and then we'll fix it. Like you guys aren't, until you say you're done, you're not done. Just because you write it down doesn't mean you all agree.
Yeah. The question of how many digits we want to carry here is kind of a
Yeah,
interesting one.
It could be like, I don't know, three decimal places might be good, or I guess 5 sig figs is what I had, or you could do 6 sig figs. I don't know.
Yeah, just go 3.
Question.
Close
Yeah.
enough. Carry everything out to 3. We started with that with the angle, so let's just do everything to 3.
That's good. Let's see. I'm
All right,
also
so
wondering, what'd you get?
for what?
Oh, sorry, what were you gonna say?
I was gonna say I've got the forces in newtons instead of as gram measurements.
Okay, nice.
Let's get them down.
For the board, it's 3.404 newtons, and for the and for the weight, it is 5.396 newtons.
Got that too. So sounds good.
Where does the board go?
Right in the middle.
Yeah, right in the center area.
That's the 3.404. Yep. All right. And so I was wondering if we have that arrow that's the arrow of tension, do we need to include the f of ax and f of y, ay up in the top?
No, because the board doesn't know those are there.
Yeah, okay. I was
Now
thinking
Now
that.
you're right. You're right that whatever those two forces are up there, because cables carry that down, they'll be the same two down here.
Okay, so it's the same, yeah, it's the same forces, but down there.
So we could break it into X and Y components if we wanted to, but
Okay. Then you probably should, right? Because like if you just call
Yeah,
this
'cause we're looking
tension
at-
right now,
Yep. That's that tension force.
'cause
And
that's
then,
actually what we're trying to calculate.
and the only other things we need to include would be the board on the wall. So we could draw the f of bx and f of yx in there.
Yep, I'll get those in there. Is your free body diagram complete? Did you miss anything? Is it all there?
I mean, besides drawing like our distances and angles, if we wanted to, that's
Yeah.
all the forces. What do you guys think? Let's see.
I'll leave them off just because they are up above,
Yeah, that's true. That gives us that.
but you guys are good. You got it
Okay.
all, like with all those. So the question is now, can you
All right. Now,
use your equilibrium equations to calculate T?
all right, here we go.
Hmm.
So I guess I'll just start with the forces in X on my own.
yeah, my first thought was just start with moment, but
Oh, we could, yeah, we could do that, or we could all kind of do something different, so we could save time, maybe.
a bad plan. The point of contact with the wall is kind of awkward. I guess you can kind of just
Oh, like what point it contacts exactly? Oh, that's a good point.
It's flat.
yeah, I mean you could functionally just call it like the middle of the side of the board, I guess.
Inside of the board. Okay, sounds good with me. And so that is the half of the CE down, right? So 2.6 centimeters down from where F of T is acting.
Yeah, and you're right, because that, where is the force of, where's T? Well, T was attached at the top of the board, and so that actually is significant. But to keep it simple, because I don't want to keep you guys any longer, and because it's going to make a fairly small difference. Let's say it's touching at the top up there.
Okay, for that one.
That's the point of contact, just to save you a little bit of trouble.
Okay.
Which would happen if the board was just a hair above 90 degrees or something of that nature.
Okay, I've got an expression for force of X, and that's got two unknowns in it, so still gotta do some work.
We'll write it down, Ben.
You write down what we got so far. Yeah, it sounds good.
Yeah.
So I've got well, f of bx equals, and then minus force of t times the cosine of 37.667 degrees, and that all equals 0. So I think those are, oh yeah. And I think that would be all in the x direction. Yeah, it looks like it. Okay.
Can always change it. So anybody that's got something to write down, let me know and we'll write it down.
Sounds good.
You guys okay staying a little after? Sorry, we're going long.
Yep.
I'm with it.
I mean, not for too long, but yes.
Yeah, probably till like 12:30ish.
Yeah, we'll have it here in 5 minutes, I think.
Okay. Okay, I think I got force of y's written out too. I don't know if anyone else has done that as well, but you can see if this is the same thing you got. I got, let's see. So f of by plus t times sine of 37.669 degrees, and then minus our 5.396 newtons, and then minus our 3.404 newtons, all equal to 0. And we're just going to do our moments. See if that. Oh, wait, let's see. Yeah, we still got 3 unknowns in total. So,
Yeah, it's in the bar. 3 unknowns. So we can't stop.
All right. Well, I used the moment around B to find the
yeah, that's smart. Okay.
tension of Y, but I'll wait to see what you have so you can double check your answers.
Let's write
Yeah.
down what you got, Landon, and then we're
Yeah.
All
ready.
right. I've got okay, well, we've got a lot of calculations here. Want me to just write it all out?
Yeah, just
Or
I'll write it in. You
all
just
right.
do it
So
out. Great.
negative 3.404 times I kept a couple extra digits here, 0.07545.
.07545.
Minus 5.39 newtons times 0.1319. Plus the tension Y times 0.1509. Equals 0. Yeah.
Okay, I wrote what you said.
And let me double check on my work real quick.
Yeah, I think I'm getting the same thing so far. That makes sense.
All right, and then so it should just be 0.1509 times the tension Y is equal to about 0.967. Yeah, a couple more sevens. So the actual final tension of Y appears to be about 6.413 newtons.
Okay. We'll be able to get our regular tension from that, so that'll be good.
Did I write that down right, Landon? 6.49313.
413. Yep.
Yeah. Yeah, I got pretty much the same thing for TY, so it's good.
All right, what's your proposal for the tension on the string that the spring scale read?
All right. So that will be would be 6.413 divided by the sine of 37.669, which will be okay. I got it for doing 3 sig figs, 10.5 newtons.
Say again?
I got 10.5 newtons. Does that make sense? Oh, maybe I did that wrong because it should be. No, I guess that would make sense. Should be quite a bit more than the Y force on it.
Take a look.
Your career is hanging in the balance. Tell me when you guys are ready. Tell me if you agree with Ben or disagree.
Yeah.
If you all agree, that's a good sign. If you disagree, then you got a big conversation to have.
Of course, it would be good to check that if we could with the other numbers here.
Let's see. Six.
Anybody agree or disagree with anything?
I disagree, but I'm not sure if I'm right yet. Give me a minute.
What'd you get? Just so other
Yeah,
people
what do you
think about it.
yours?
Let me double check this real quick. Am I in degree mode? Yes. Okay.
Okay, so let's maybe.
Uh, hmm. Yeah, no, this answer seems way too low. Never mind. I've definitely got something wrong somewhere.
What'd you do for your answer?
I just plugged the tension y into the some of the forces in y equation, and then just solve
Oh,
for
it's
tension.
for FBY. Wait a minute. Well, we couldn't.
Oh wait, hold on. What? That's by. Oh shoot. Never mind. I'm really dumb.
Oh, yeah, you just should didn't. Oh, that's
Yeah,
all right.
yeah.
Yeah, trying to figure out the why, which.
Yeah, disregard all that.
Well, actually, I guess you could do the moments around C, so you could double check if you wanted to find that out. But that wouldn't work.
Okay, let me think.
Yeah, it is interesting that you don't have to just do the moment around B. It's sort of the most natural place to do it because you think of it as lifting up and so forth. But yeah, I mean, in the interest of time, if we had,
That was the easiest place to do it.
but if you did the moments around C, then T will have no tension or T will not be a factor. The moments around C would let you find the force of BY,
It's true. If you wanted to find that, that would what you do. Yeah.
which of course, if you had the force of BY, then you could use it in this equation right here. Once you
Yeah.
do it, to solve for T since it has two unknowns.
So it's true. That would allow you to find that. So you could, yeah. So it could have been a backwards way to kind of find T, but this was the shortest one was just to do MB. You didn't even need those two previous equations.
Yeah, and it took out the force of BY and the force of BX, which we didn't know.
Yeah.
And nice. Took out the ones we didn't know, and it only left in the one we wanted to know. So
So that was, yeah, Landon's a good idea to do. Do it around B. That was smart. So let's see. Okay. Yeah, I'm getting it 10 point. Checked it again. I think it's 10.5.
so you see no mistakes in 10.5.
But yeah, I mean,
Have an answer for force of BX and force of BY by chance?
oh,
Is that a curiosity?
I haven't tried to get those, but that's a good idea. I should try that.
that wasn't you had to calculate, but it's force of By is particularly interesting to me here.
I'm getting 2.38 newtons for that. Let's see if other people get the same thing.
Feels like kind of a lot. I mean, not like the answer, but just like an impressive amount. You know what I mean?
That, yeah, of that friction. Yeah, that does seem like quite a bit. But of course, the tension of the string was pretty big too.
Well, it's interesting because, yeah, the tension in the string is pulling it back against the wall really hard, but that's the next thing we're going to talk about in class is friction. And it's pretty interesting. Notice we got a positive answer, which means my arrow drawn up was sort of drawn in the correct direction. And that's exactly the force that's built up there as a part of friction. If you think about it, if you put the board against the wall, it's going to fall, right? If it's not touching, if it's just touching the wall, it's just going to fall. But if you push it against the wall, the harder you push, the more friction that you get. Have you ever tried to push something on a concrete floor? If it's really light, it slides really easy. But if it's really heavy, like a box or a piano or something really heavy, it does not want to slide. And so the amount of force pushing into the wall actually creates a friction component. And interestingly, that has to be here in this problem, or this wouldn't stay there. That whole side would just fall under the weight of the beam itself. So it's kind of interesting that force developed, even though, I think about the attachment, I think, well, it isn't attached. So it's not a smooth connection. Does that make sense? That's what the book means. It's not smooth. There's friction there. And thank God there is, because if there wasn't, this wouldn't stay. It would fall and we wouldn't be able to do a job.
I got, for the force of Bx, I got 8.31 newtons. So that's even bigger.
Yeah, I had a real world application with this particular problem a little while ago over the summer, where I was trying to create a device that had to basically attach to a whiteboard. And these things are relatively heavy.
Mhm.
So my idea was I'd create like a 3D printed base and embed a magnet in it.
Mhm.
But it ended up being a lot more trouble than I thought it would be, because even a really small amount of material between the whiteboard and the magnet would really decrease the force of the magnet a lot.
Right.
But
Yeah.
the magnet itself is also really smooth. So having the magnet directly contact the board was a big problem too, because it would just slide down. So the eventual solution I came up with was actually just taking the magnet and putting it like painter's tape on top of the magnet, because it was a rough enough surface that
Nice.
would still work, but it's still thin enough that it wouldn't impede the magnet too much.
Nice job.
I think this is the answers because I'm getting the same stuff.
The same thing? Oh, good.
Yeah.
You got 10.5 and everything.
Yeah, I got 10.503, and for the FBY, 2.3836. I got, wait a second. Yeah, same thing. And I'm gonna look at the FBX right now.
Yeah, that one's pretty fast to solve.
Well, I want to let you guys be able to go since a couple of you agreed. You ready to know what the spring scale read?
What did it read? Oh, yeah.
Dong.
Moment of truth.
Yeah.
Oh, 10.2. Wow.
Isn't that cool?
Wow.
Now, of course, we took our measurements, and you think about it, that's actually closer than it should be, really.
Yeah, that's actually.
All the measurements were taken, by a human, if you will. The students took the measurements. We trusted the scale to actually weigh things correctly. The spring scales aren't a super accurate, tool. They literally just pulls on a spring, and it's the concept we've been talking about. Because the spring scale will read the newtons based on how hard you pull, and so that's pretty sketchy. And So frankly, that it's that close is actually pretty cool. But I just think this is neat because you have to get all the measurements yourself, and there's no force in this. All there are is grams, and you know if you don't convert correctly, so to get all of this to actually work like it did, pretty darn cool. And I think this teaches you a lot. So next time when I see you, we're going to pick up this concept of friction and how friction at this, excuse me, I get the hiccups now. Friction at this joint over here where that was hitting the wall, that friction, it is proportionate to how much force is on it. Force is proportionate to friction. You double the force, then you'll double the amount of friction that's created at that joint and so forth. And kind of, you know, what things you can do to control. And again, we're going to do the same kind of things in class. I have an app on my phone that'll tell you what angle something is at. And so we're taking like a calculator like this and sitting it on a table and tilting the table up, and it just stays there until at some point then starts sliding. And so you can actually take all your own measurements and figure out friction coefficients. It's kind of neat stuff. Anyway, good job. I think you guys made a ton of progress today. I think that's really cool that you're all able to weigh in on the same answer. And now you have a job tomorrow still. You didn't lose your engineering agency. So.
All right. Bye, Doug. Thank you, everybody.
Right. Bye, everyone.
Hey, Doug.
Yeah.
So I am getting really